You know, when you think of physics, you probably picture geniuses in lab coats scribbling on chalkboards, right? But what if I told you it's not just for them? Really, physics is just a toolkit, a set of tools for understanding the fundamental rules of the world all around us. So let's open up that toolkit and see how just a few of these basic tools can help us make sense of everything, from why a $1 billion spaceship might crash to, how a simple seesaw actually works. But first, let's talk about what happens when you don't use the tools correctly. It's a bit of a cautionary tale. Back in 1999, NASA's Mars Climate Orbiter, a mission worth a staggering $125 million, was just lost. It literally burned up and disintegrated in the Martian atmosphere. And the reason why? It's almost unbelievable. One engineering team used metric units, while another used imperial units. A simple, basic conversion error, the kind of thing you learn in high school, had absolutely catastrophic consequences. And this whole disaster brings us to the very first and maybe the most fundamental tool in our entire physics toolkit. Because that incredibly costly mistake, it wasn't about some wildly complex orbital mechanics. Nope, it was about getting the basic language of physics right. And that is the absolute first thing we have to master: the language. In physics, that language is built on units and conversions. It is the essential vocabulary you need to have down if you want to describe the world accurately. I mean, think about it this way. Converting meters to millimeters, or grams to kilograms, it's just like knowing the difference between there, and there in English. If you use the wrong one, your entire meaning gets lost or twisted. Well, for NASA, that lost meaning translated directly to a lost spacecraft. Okay, so that raises a pretty important question, doesn't it? Is there a way to check our work? You know, like a spell checker for physics equations, something that tells you if what you've written down even makes sense on a fundamental level? Well, turns out, yes, there is. It's called dimensional analysis, and this is our grammar checker. It's this incredibly powerful but simple tool that lets you check if the units, or dimensions, on one side of an equation logically match the units on the other. If they don't, you know right away your formula is broken. And this slide shows it in action perfectly. Just look at the left. If we plug in the units for each part of the equation, we see that the second squares cancel out, and that leaves us with meters per second on one side and just meters on the other. They don't match. The equation is just fundamentally wrong. But now look at the equation on the right. When you work through the units, boom, they match up perfectly on both sides. It passes the grammar check. Okay, so let's move on. Let's grab the next tool in our kit. Once we've got the language down, we can start talking about the action, all the pushes and pulls that govern pretty much all motion in the universe. We're talking about force. And right off the bat, we have to clear up a super common point of confusion: the difference between mass and weight. Your mass is just the amount of stuff you're made of. It's the same whether you're here on Earth, bouncing on the moon, or just floating in deep space. Your weight, though, that's the force of gravity pulling on all that mass. So an astronaut has the exact same mass everywhere, but they weigh a whole lot less on the moon, because the moon's gravity is just weaker. The key takeaway: mass is constant, but weight is a force that can change. Now, to see how these forces interact, let's look at a classic problem. It's a bit of fun. We've got a big ogre on one side and a goblin and a troll on the other. They're in an epic tug-of-war over this huge treasure chest. So who do you think is going to win? And this chart breaks it all down for us. You can see the ogre is pulling with a mighty 1,200 newtons of force. That's a lot. But on the other side, remember, their forces add up. The goblin's 400 newtons plus the troll's 850 gives them a combined pull of 1,250 newtons. The bar chart makes it really clear. They're just a little bit stronger when they work together.
So the goblin and troll team wins. The overall force, which we call the net force, is just the difference between their pull and the ogre's pull. And that comes out to 50 newtons in their favor. That 50 newtons is the force that's actually going to get that chest moving.
But forces don't just push and pull things in straight lines. They can also create rotation. And this brings us to our next tool: torque. Torque is really just the scientific word for a turning or a twisting force. Understanding this is key to everything from how a simple wrench works to how a massive construction crane can lift things. This wrench is the perfect way to visualize it. When you push down on the handle, you cause the wrench to turn around a pivot point, in this case, the nut. That turning effect is torque. And here's the really cool part. The further away from the pivot you push, the more turning force, more torque you get for the exact same amount of effort. And here's that exact same principle at work, but in a balancing act. How on earth can a lighter object balance a heavier one? Well, it's all about leverage. By placing that lighter 170-gram mass much further away from the pivot point, it creates a turning force, a torque, that can perfectly cancel out the torque from the heavier 200-gram mass that's closer to the center. It's literally the physics of a seesaw in action. All right, let's add the final tool to our kit for today. It's a force that is absolutely everywhere, an unseen opponent we have to deal with in pretty much every single physical interaction, and that's friction. Okay, so here's the scenario. We've got a 5-kilogram box just sitting there. We're going to push on it with 15 newtons of force. Now, we happen to know that the coefficient of friction for the surface it's on is 0.4, which is really just a fancy way of saying how grippy the surface is. So, the big question is our push strong enough to get this thing to move? Well, to answer that, first we have to figure out the maximum possible force of static friction. That's basically the strongest grip the floor can exert on that box to keep it in place. And after we do the calculation, that number comes out to 19.6 newtons. That right there, that's our magic number. That is the force we have to beat. And there's our answer. Our push is only 15 newtons. That's less than the maximum static friction of 19.6 newtons. The unseen opponent, friction, wins this round. The box isn't going anywhere. We simply haven't pushed hard enough to break its grip. So there you have it. A basic, but I think you'll agree, an incredibly powerful physics toolkit. We've covered the fundamental language of units and dimensional analysis. We've looked at the action of competing forces to find the net force. We've seen the awesome power of leverage through torque, which, by the way, is sometimes called a moment. And finally, we've wrestled with the constant, everyday resistance of friction. Look, these aren't just abstract ideas in a textbook. They are the literal rules that govern our reality every single day. So the question I want to leave you with is this. Now that you have these tools in hand, what invisible pushes, pulls, turns, and grips will you start to notice at play in the world around you today?